Hi, so this is my first video about teaching. So I hope this thing work well. So later on in the future, we're gonna make more videos, something like this. Okay, so for lab 6, the problem is about finding the minimum spanning tree. Alright. So before jumping to spanning tree, you have to understand what is graph. What is graph? And then you go to what is tree. And after you know what's a tree, you will know you have to understand what is the MST or the minimum spanning tree, which is the problem of the lab 6. Okay, so let's start to explore what's a graph. So you see the image on my left side, it's actually called graph. So a graph is something that have like the node and the edges. So the graph is like the map in real life. See, like from the city, you go to this city, and then you have some sort of like distance between two cities. You have distance between city 2, city 4, between city 4 and city 3, between city 1 and city 4. See, you have like distance. So graph is just kind of like the representation of the real map that we're using nowadays. So Google Map, they're actually using the graph, and then they just putting some image on top of the graph so you can have like some user friendly. But underneath it, it's actually a graph that look like this, in the sense of like computer science. So the graph, so let's write here. The graph is something that has like nodes and edges that connect together. Okay, so that's the definition of graph. So now what's a tree? So you can see in real life a tree look like this. See a tree, this is a tree, this is a tree, this is a tree, this is a tree. So this is a tree, right? And you can see like the kind of like the connection between the branches. This looks like the node, right? See, this is like a node, like the connection between branches, connection between branches, the connection between branches. You see, and this is like a node. Node can be represented as city, right? And branch can represent like the edge. So basically, the tree, it just look like the graph. See, kind of like similar. So the first thing you can tell is like the tree is actually a subgraph because it's similar like the graph. See, they have node, have edges. The branch represent the edges. See, from node here to node here, you have kind of like the edge in between them. You have a node here, and then you have a branch in between of them. So it's kind of like a graph in general. So tree, the first thing you know is a subgraph, right? And what? So let's form a tree in this big graph right here. So from this graph right here, I can form a tree like look like this because it's a subgraph, right? So you can have one here, and one here. See, now you have a tree. See, from the tree that only like from 3 to 1 to 4, and 4 to 2. This can be a tree. And also this can be, you can form a tree look like this. Like only 2 branches, like from 3 to 1 and 1 to 4. This can be a tree itself. So this can look like this. Yeah, so this can be a tree itself. And also you can connect this thing together as well. So that can be also a tree. See, this can be a tree. But this thing right here is a whole graph. So you can form a tree based on the graph. So the tree is kind of like inside the graph. So that's why it's called subgraph. And if you connect this thing, it's still called a tree as well, because it's inside. Okay. So delete it. Let me redo it. Actually, okay. So you can say that, okay, tree actually a subgraph. A subgraph. And also, yeah. So now the last thing we have to do is, what is the MST? So look at the name. You see MST actually the minimum spanning tree. So you see a tree. So you can know that like MST actually a subgraph. It's because it's a tree. Tree is a subgraph. So they're the same. But what's a minimum spanning mean? Minimum spanning mean the the lowest total weight. So minimum, or maybe MS, minimum spending, mean the lowest total weight. And what's the weight? Weight is actually the cost that you move from one city to another city. That's called weight, or the distance, and anything you prefer to call. So, but I would say the weight. I prefer to say weight. So you find the tree that, like, when you add up all the distance, you have like the smallest total distance. So you picked up a tree. Let's say I pick up this tree right here, right? And when you add it up, all the three distance, those three, the total gonna be 6. So that's a minimum. That's not a minimum spanning tree. That's like one of the tree. So see this tree right here, total distance gonna be 6. Okay, and you can form another tree, like let's say from here to here to here, right? And then you add it up, it's gonna be 4, 3, and 2. So look like 9. See, and you can form another tree, like from here, here, and maybe here. So your total gonna be 3, 2, 2. So you add it up, gonna be 7. See, there's a lot of like tree combination that you can form from this graph right here, and your goal is like to pick out that, like, all that combination. You try to find the one with the smallest total weight. So that's that. So that is the goal of the minimum spanning tree problem. Like, out of the all tree combination, find the one with a minimum span, with a minimum total weight. Okay, so now, but the minimum spanning tree also have some criteria that you need to careful. So you see a tree, you can form a tree like this, right? From 3 to 1 to 4, right? It's only go like over like 3 city, 1, 2, and 3, right? That's a tree. But for the minimum spanning tree, the first criteria is like it has to go to like every node in the original graph. It has to go to like every city. So the previous tree, like this one right here, is failed to satisfy this condition because it only go over like 3 nodes, like 1 and 3, right? But this one right here can be a candidate. It's not a minimum spanning tree yet because we didn't check the total weight with order, but this can be a good candidate because it have like it go over like 4 node. You see it? 4 node, and there's also a subgraph, right? And the second criteria is like when you have the tree, when you form a tree, it has to be like acyclic. So acyclic. So what's acyclic? Acyclic mean like the tree doesn't form the cycle. So you see this thing doesn't form a cycle. But what happened if you have a tree like this? See, like you'll go from city 1 to city 4, and some city 4 you go to 3, 3 you back to 1. You see, it's from a cycle. So this is not satisfied too. It should not be. So the one recognition of a minimum spanning tree is like it should not form a cycle. Therefore, this thing right here will not be the candidate. So this one is a good candidate because it's go first. It's go like over like all the node in the graph. 1, 2, 3, 4. Then the graph have 4 node. It go over 4 node. That's good. And also you didn't see any cycle. Like it's going one straight line. You see, there's no like something looking back. So it's fitted. And also it's a subgraph. So now let's define the final definition of MST. MST first is a subgraph. Second is no cycle. See, there should be no cycle, otherwise it's gonna loop forever. And also, the last one is have to like go like it have to like contain. It have like contains all of the nodes of the original graph. So three condition, a subgraph. So subgraph, no cycle, and the third condition is contain all the node in original graph. So the MST need to satisfy this three condition. Okay. So let's go back. So after you know all the basic theory, concept, definition, terminology, let's move on the main problems, like how to find the MST. So the first way is using brute force. Brute force means like you try to use to find all the combination, and then you pick the one of the best. So basically, in the graph right here, you try to find all the candidate. You try to like generate all the candidate like combination of the MST. So this one can be one candidate right here. This one. This one can be a candidate. This one can also be a candidate. Right. And this one right here also can be a candidate. So let's try the brute force way, for example. Okay, so let's say right here, this one. Let's check the MST condition. Is it a subgraph? Yes, because it's go over like it's inside the original graph. And is there any cycle? Seem not to, because it's going one line. Yes, does it contain all the node in the original graph? Let's see. 1, 3, 4, 2. Yeah, let's go all the 4 node. So it's actually contain all the original. So it's actually the MST candidate. So now let's see that the total weight is going to be 1, 2, 3. So the total is going to be 6. So let's write over here 6. Oh. And now let's check another candidate. So this one can be another candidate. So let's first check. Is it a subgraph? Yes. Is there any cycle? From 1 to 3, from 1 to 4, from 1 to 2. There's no like connection between 2 to 4. There's no connection between 4 to 3. So there's no cycle. And does it contain all the node of the original graph? Yes, it goes to CD1, CD3, CD2, CD4. So it's like the good candidate of MST. So now let's find the total weight. It's going to be 4, 2, and 1. So it's going to be 7. So let's write 7 here. 7. So now let's find our candidate. Let's try this right here. It's a subgraph. Yes. There's no cycle. Yes. It's only go one path. There's no connection between 1 and 3. And does it contain all the node? 1, 2, 4, 3. Yes. So let's add up the total weight. It's gonna be 4, 3, and 2. So it's gonna be like 9. So right here 9. So in the end, let's say you find all the combination. That's what I do here, etc. right here. After you find all the combination, you're gonna pick the best. So far, I will say this one is the smallest. So that's why the one that would like the 6 total weight gonna be a solution, and which should be this guy right here, as I remember. So this is your MST. It satisfies all the 3 conditions, and it's at the smallest weight. Right? So that's a brute force weight. And brute force weight is kind of like a lot, because you kind of like generate a lot like a 3 combination, and sometimes you have a huge graph. It's kind of like a lot like memory consuming and time consuming as well. So brute force is not recommended. That's why smart people in CS department or something in the past, they're using the second approach, which is better than brute force, called greedy algorithms. So what is greedy? When you see greedy, what do you think about greedy? Like, what's the definition of greedy? So greedy mean like you kind of like want everything best for you, want everything best for you, pick the best for you, right? Anything you want, like best for you. Like you only care about you. Like, oh, I choose this one. because it's so tasty. It's good. I like it. So you want it for yourself. You don't want to share it anyone else. Yeah, like that. Like you want to pick the best thing for yourself. Okay. So how greedy apply to this problem? So this problem, your goal is like try to find the minimum, right? So when you create a tree, the MST, you have to consider like, so how can you have the minimum total weight in order to have a small sum, like to have a small sum, every element inside has to be small, like x has to be small, y has to be small in order to have the small sum, right? Like x small, y has to be small too, and z has to be small too. Like your goal is like trying to find all the smallest elements. So in the sense of this problem right here, you're trying to find the smallest path to go, and you try to avoid the long path. So greedy in this case mean like, okay, I only pick the shortest path to walk because that's best for me, because my goal is like to find a minimum spanning tree. So you greedy in this sense, like to find the smallest path. Okay. So greedy algorithms in this problem mean like find the smallest path to walk. Right. Okay. So let's move this thing down a bit. And for the greedy algorithm, there's kind of like actually two type of greedy algorithm of this type problem. It's going to be Prim. Let's give it a color and a different color. Prim algorithms, and another one's crucial algorithms. So for in Blackboard, the TA and professor, they kind of like using Crusoe, and they put like pseudo algorithm on the Blackboard. You can check it if you want, but for me, I'm using Prim because I like it. I mean, just my reference, but you can try Crusoe if you want. But in this video right here, I will only explain Prim algorithm. Okay. So how Prim algorithm work? So Prim algorithm, it's just like the name of greedy, like you pick the smallest, that's best for you. Okay, let's try Prim. So let's see how Prim works. Let's copy the graph here. Oh, never mind. I have a graph. Move this graph right here. Okay. So let's move this here. Okay, let's clean it a bit. Okay. So this is about Prim. Prim algorithm. So how Prim gonna work? So because it's greedy, you try to pick the lowest path. So when you look at this image right here, the lowest path you see so far is like number 1, the lowest compared to others. See, 4, 2, 3. 1 is the lowest. So you greedy, pick this guy. Bam. So this is your first path. Okay. And now you try, and then now you have the first edge. Now from 1, you can say like, okay, you can walk to here. And from 1, you can also walk to here. And from node 3, you can also walk to here. And now you try to pick the lowest path because you greedy, right? So you have 3 possible paths to walk next, like 4, 2, 2. And the lowest is gonna be number 2. And there's 2 possibility. And you can pick any of them, that's fine. Because they are either way you walk, you still have the smallest. So I will pick from 1 to 4. So from 1 to 4. So now you walk. Okay. And now you try to explore to see the next move. So from 1, you can still go to 2 again. See, still go to 2 again. And from 4, you can still go to 2. And from 3, you can still go to 4. Okay. Now, let's see. So now, again, greedy means you pick the lowest path. So 4, 3, and 2. You kind of like pick 2. But wait a second. Why 2 here is not possible? Let's say you pick 2, and your life gonna look like this. But now you see what? You see a cycle. It's a cycle. It's a loop here. But our condition for MST is like no cycle. So that path is short, but it's not valid. So you rule it out. Right? So you rule it out. This is not possible path. Therefore, you cross this. So your two possibility left is 4 and 3. And 3 is kind of the smallest. So this is your final path. And so now you walk from 4 to 2. So this is your final path. And after you walk to 2, right, you can look at this. It's already go over like 4 nodes already. So that's why you stop, algorithm stop searching. So your final MST is going to be 1, 2, and 3. You see that? By using Prim algorithm, you're doing like, you are creating MST as you're searching. But the brute force way right here, you have like generate like all the 3 combination, and then you pick the smallest one. This kind of like create a lot of like combination. But this one right here, you get the MST like right away. You're finding as you're searching. Okay, that's the Prim algorithms. Let's get another example. So because you see in here you kind of have 2 possibilities, right? So let's do it again with going another way. So when you look at the graph, you greedy, the smallest you see is 1, so you go here. Okay. From 1, you can see 4, you can see this, and from 3, you can see this. Right. The last time we kind of like pick the top. Now we pick the bottom. We can pick the bottom like edge. Because 2 is smaller, is the smallest compared to like 4. So you gotta go this way. So now let's say we go this way. Go here. Okay. Now from 4, now let's continue. From 1, you can see this path right here. From 4, you can see this path right here. And from 1, you can also see this path right here. Now if you see it, 4, 3, and 2. 2 is the smallest. You want to walk here. Let's say you walk. But after you walk, you see that it's from a loop. It's not valid. So you don't want to go to 2. Therefore, you cross it out because it's from a loop, which is not the MST criteria. And you have left is 4 and 3. And 3 is the smallest, so you prefer to walk here. So therefore, your final MST is going to look like this. 3. And after that, you see it's already walked by like 4 nodes. So you stop because the condition of MST is like you have to be 4 nodes. All the node original graph, I mean. So it's already done. So this can be, this is finally your MST solution. The total edge is going to be 1, 2, 3, it's going to be 6. See, it's still 6. And the previous one we have like this way, it's still 6. They both 6. So they both like valid. They both like minimum spanning tree compared to other like large tree. See, so this is the Prim algorithms. That's how it works.